So let's begin with this lecture. So the issue for today is dealing with limits. What are limits? And the first thing I would like to review is what is zero specifically. So already, if you imagined prehistoric times, the most strange number, and the number that you will find not so comfortable perhaps, is zero. So imagine that you go to your cave, back to your wife, and she asks you, how many buffalo did you get? And you say 5. So she's very happy, right? But what are you going to tell your wife when you found 0 buffalo, right? No buffalo at all, right? That's actually not nothing. If you tell her that you have gotten 0 buffalo, that's not nothing. Here is why. So first of all, 0 plus any number is that other number. That's the definition of 0. Okay, and from this information and from foiling or from expanding parentheses, we will show that 0 times x is in fact 0. So how do we know that? Okay, so 0 times x equals to 0 plus 0 times x, which is equal to 0 times x plus 0 times x. And then we can just cancel, right? So what can we do? We can just subtract 0 times x from both sides, and we get that 0 equals to 0 times x. In case you have not seen such a proof, that's a simple proof that 0 times anything is 0. It's not just some philosophical thing, okay? And now, why can't you divide by 0? So if you think about 5, right? What is dividing by 5? Think about 1 divided by 5. That's simply a number that when multiplied by 5, it gives you 1. Could there be a number of the form 1 over 0? By its essence, it should be a number that if you multiply it by 0, you get 1. Okay, but here is the problem. We just showed the following. We showed that 0 times any number. So if this is a number, it will be 0. So this would mean that 0 times this number is 0. And on the other hand, this 0 times 1 over 0 is 1. 1 does not equal 0. Therefore, 1 over 0 is undefined. You understand? This is a limit. It's chapter, possibly in your book, it's 2.2. So, but sometimes, and this is now the part where calculus begins, you really want to divide by 0. It's very important. And hopefully you will understand this problem. For now, we are doing it intuitively. So this is differential calculus, the velocity problem. So suppose the following is your task. You have a car, and the car was recorded to move on a straight line. It's a linear motion, and you have a YouTube video of it, right? You don't see inside of the car. You only see how the car moves outside. And your goal is to determine how fast the car was moving when it passed the red light. Okay, this light, when it moved through it, how fast was it moving? So in general, right, what do you see? You see that the car is a function of time. And you know that because as you move the time cursor, the car will obtain a new position. And that new position will be definitive for time. So in other words, the car will not be in two places at the same time. Okay, so at 0, let's say that this is the table that we have obtained for some of the values. Let's see if you can guess the actual function. So at 0, when the video begins, the car is 1 unit of distance on the x-axis. It will be here. Then at 1 second into the video, the car is 2 units of distance. At 2 seconds, it's 5 units of distance. At 3 seconds, it's 10 units of distance. What I'd like you to try to do is, given this information, can you guess what might be the exact position of the car for any moment of time t? Calculate, please. Thank you, Kirill. It's t squared plus 1. Naturally, from this small amount of information, maybe it's not correct, right? But this is definitely a simple function, and it definitely agrees with the patterns observed. Okay, so that's our formula. X of t is equal to t squared plus 1. Now realize what this means. This tells you how time is transformed into position. Once I know the time, I know exactly where the car is. So far good? So guys, you see, you are watching me intensely, but then I'm not sure if you are watching me with your spirit present. Okay, so most of you are quiet and I don't see your faces. Maybe you just log in and you just go away. What's the velocity of this car? First of all, what does the question mean? Anybody would like to try to talk to me? What is this velocity of the car that we're interested? We are interested in the velocity of the car when it passed this position 5 mark. In other words, 2 seconds into the video. So what is it that we're interested in? Would anybody try to explain to me?
Are we interested in how fast the car is going?
Yes, we're interested in how fast the car is going, but that's a synonym perhaps of velocity, right? What is it that that we are watching? What is it that we're trying to calculate? What is velocity to begin with? Would anybody try to explain that? It's a very primitive concept, so you see. Let's see what you would say to me.
The speed, or no?
Speed, but you see, you want to make it operational. How would I recognize it? How would I calculate it? In general, right? So you all have driven cars, and you all, or some of you, have had gym lessons, and you had to run, for example, right? So you might calculate that somebody was running at a speed of 6 miles per hour, right? What is that information? What is that supposed to be? Try to explain to me. Okay, Irvin, it is distance over time, right? And in particular, let's see what we can add to it. So velocity is change of position divided by change of time. What you assume when you say that, you might not have realized, is that, well, you assume some uniform motion. In other words, when you say that a runner is moving at 6 miles an hour, that's initial assumption. If he's moving at 6 miles an hour, tell me how many miles is he moving in half an hour? And one person says 3 miles, 3 miles. What about the rest of you guys? All of you agree it's 3 miles? How many of you have run or walked or moved? You see, so one person says it depends on acceleration, right? So just because you said that the person is running at 6 miles an hour, the half an hour might be run at a different speed, right? So when your first definition is for constant motion. So velocity, constant velocity, is change of distance over change of time. You understand? And by that, what are you trying to capture, right? It's very difficult to understand either time or motion, but we have an intuitive grasp of it. So if we have a regular measurement of time, so we want to know how much distance was covered in that time. Okay, so if a person is moving constantly, you would think 6 miles in 1 hour, 3 miles in half an hour, right? 12 miles in 2 hours if the runner is moving constantly. Do you understand? So we have a definition of velocity, but only when it is a constant velocity. Do you realize that? You see, because it's already very difficult to think what happens if the velocity changes. But if something is moving uniformly, then we describe it's this amount of distance moved per this amount of time. Why? It's a constant, notice, right? So in 1 unit of time, 1 hour, 6 miles covered, right? If I take 3 divided by 1/2, I think I have it somewhere over here, right? So 6 over 1 equals to 3 over 1/2 equals to 12 over 2. So if it's constant, I capture this constant, this perpetualness by taking the fraction, distance over time. It's very similar to what we covered in the last case, right? It's very important. That's called normalization, right? So that that means that motion, the amount of speed covered, is stable. Just like we did for the disease, remember last time, right? What they did not do is show that it's stable, right? So that's a similar concept here. So the question now is, well, is this car moving at a constant rate, right? What might you try to do to calculate its speed? We are interested in the speed or velocity at 2 seconds, or right at 2 seconds. So I can try this formula, right? I can try the position at 2 seconds minus the position at 0 seconds divided by the elapsed time. So position at 2 seconds, we had 5. Position at 0 is 1. So 5 minus 1 over 2, that equals to 2. Right? So if I do this ratio, what I did here is, again, I measured, I took 2 position intervals divided by the time that has taken for the car to move from one position to another, right? I just did change of position over change of time. Guys, I have to be sure you all understand up to this point, yes? So I got 2. Would you say that then 2, if it's, let's say it's miles and maybe time is in hours, is it 2 miles an hour? Or 2 miles a second, you know, in whatever measurements? Is it 2 units of distance divided by 1 unit of time? Is this the right velocity for the car? So Irvin says yes, it's the right velocity. Well, units, let's say units are given, right? So let's say unit of distance, maybe it's meters per second, right? So it's 2 meters per second, okay? And Joshua, one person says, I don't think so. Okay, you understand under what assumption did we do this, right? So if an object is moving at uniform speed, it's enough to take 2 positions and divide by the amount of time taken to move from first position to second position, if it's constant. You remember, that's what we did with the 6 miles an hour. What is 6 miles an hour? You take 1 position, let's say the person is in position 1, and then in 1 hour, the person will be in position 7. 7 minus 1 will be 6 divided by the unit of time 1, okay? Or if I notice that, let's say, the position changed from 1 to 13, all right, then I take 13 minus 1, I get 12, and I realize the amount of time it took for this, for the new position to be attained was 2 hours, okay? So in here, I do this calculation, and I obtain 5 minus 1 over 2, and I got 2. But look at it, I can take a different position, right? I can take position 1 and 2, and I take the difference between them and how much time elapsed between moving from x at 1 second to x at 2 seconds. Well, exactly 1 second elapsed, so it's 5 minus 2 over 1, it's now 3. Notice it's a different number. What does it tell you? If it's a different number, it tells you the car is what? Oh, it's already on the board. The car is not moving at constant velocity. You realize that? Because if it were moving at constant velocity, the numbers we would get here and here will always be the same. Any increment of time will produce the same amount of displacement. But here we have a small increment of time, produces quite a lot of displacement. So the car is not moving at a uniform velocity, okay? So now let me ask you a few strange questions. So does the car have velocity, right? Does it at all have any velocity? And
Yes.
so a bunch of you say yes. I want to see that you respond, guys. Write something or talk to me, please. Appreciate it. So all of you say the car has velocity. That's very nice. Tell me then, what is it that the car has? So you say it has velocity, right? But that's wonderful. But what is it that it has? And how do you know it, that it has velocity? And let me confuse you even further. If I pause the video, the car is not moving when I pause the video. Does it have velocity when I paused it? Or does it stop having velocity?
No,
I think the car has.
velocity.
I think the car has different velocities at different times because it still has to accelerate or decelerate. So speed up.
Okay, it has velocities at different velocities at different times. I heard another voice. Somebody else was speaking. What was?
Oh, no, I just said that even if you stop the video, that doesn't mean the car would stop having velocity because it's a video. Right?
Wonderful. But then what is it that the car has? And try to answer it in a very, very simple way, if you can, right? What is it that the car has? And how do I notice that it has it? You all say it has velocity, but then you're not able to tell me what is it that we have.
I still don't get the question.
Well, you said the car has velocity, correct?
Yeah.
Now, if I said the car has Chumwick, you start asking me perhaps what is Chumwick, right? Similarly, here I'm asking you, what does the car have? You say it has velocity. What is it? You understand my question? You see, you feel that you know what's velocity, but then you're not telling me what it is.
How much ground it's
So you say the
covering?
car has something, right? What is it that it has? And how do you know it has it?
Is it how much ground it's covering? Or
But
no?
exactly at t equal to 2, right? I paused it at t equal to 2. Does it have velocity at t equal to 2, at 2 seconds? At 2 seconds, it passes the red light. At 2 seconds, it's right by the light, which is at position 5, right? 2 seconds, 2 squared plus 1 will give you 5. And that's where the light is. Okay? So what is it that the car has? That's the very complicated question. Or maybe not very complicated. How many of you have a license? How many of you drive? Wonderful. And you see, what is the speed limit in many places in New York these days? Wonderful, you know 25 miles. So how do you know you passed that speed limit? What do you do? Meter, speedometer, brilliant. That's exactly what the car has. It has a speedometer, and the speedometer is pointing to a certain value. Or maybe it's a digital speedometer, then it displays a certain value. You understand? So when the car was moving, the speedometer is always pointing. There is this arrow pointing to a particular speed, particular velocity. Yeah. The question now is, when I want to know instantaneous velocity, this is what I want to imagine. I want to imagine that there is a camera. You see, here is the picture of this car. I see it from the outside. I do not know what's happening on the inside, but on the inside, I presume there is the dashboard and there is a speedometer. I want to reconstruct what the speedometer was showing. Since I recorded it from the side, I've seen how it moves. I have it. I have the formula by which it moves. I want to reconstruct the speedometer. Now notice when you press pause at 5, you don't imagine that the speedometer stops displaying the number, right? You can imagine you have taken a photograph right at that moment of the speedometer, of the dashboard, and you can see what was the velocity with which the car was traveling. So velocity is the speedometer. Okay, that's exactly how I measure it. The instantaneous velocity is what, for a given moment of time, the speedometer is pointing to. Now, how might I reconstruct this speedometer? Notice that my velocity is not constant, which means that if I allow some time to elapse, the speedometer will likely change. You can see that here I took 2 positions divided by time. I see we got 2. Let's say 2 units of distance divided by 1 unit of time. In other words, if we measure it in meters and in seconds, so if time is in seconds and this is in meters, then we see that the car is traveling at 2 meters per second. That seems to be the calculation here. If it were traveling at a constant speed, it would be traveling at 2 meters a second. But another calculation gives us 3, which tells us that the car is not traveling at constant speed. So far, so good? So how do I reconstruct? Any ideas, right? So you are here scientists, right? And what would you do if you had this video in front of you? How would you try to figure out what is the speedometer showing at 5 when the car passes through 5, or at time 2? How would you try to reconstruct it? Guys, if you have noise in the back, please mute yourself and pay attention to the lecture. I'm not sure what is that you're doing. I mean, well, Plug 5 into the equation at t, what does it mean? So here is a video. You are doing criminal investigation. You want to know how fast this perpetrator was passing the traffic light. What is it that you do? In other words, you don't have access to the speedometer. How do you figure it out? Do you understand my question, guys? You don't need to be very, complicated or very mathematical here. I just asked you, here is a video. You really want to know how fast the car is moving past 5. How would you try to reconstruct this information?
Wouldn't you plug in 5?
And what would that give us? Plug in instead of what?
Wouldn't it give you, wait.
So remember the formula, it's t squared plus 1. So if you plug in 2 instead of t, the car is at 5. So we know the position. Our problem is to figure out how fast, the speedometer. What would you do?
26?
Sorry?
If you plug in 5 into t to the second power plus 1, wouldn't it be 26?
Yeah, but why would you plug 5 instead of time, right? We're interested in time 2.
Ooh,
Time 2, the car is at 5, right? So definitely we're interested in time t equal to 2, right? And what would you do with this time? You see, I'm pointing to it, right? If I pause at 2, the car is passing the light, the traffic light. What do I want to do next to figure out what's the speedometer showing? It's okay. Think about it, guys. No ideas, or you just all asleep? It's not important enough, perhaps, at the moment for you guys, right? I think you would have figured it out if it were life and death. No, why 5/2? So again, what is velocity measuring, right? We need to observe a change in position and divide by the required change in time, right? So velocity is always change in position. So here is a given moment of time, one position is noted, another moment of time, another position is noted. And then we take the difference in positions divided by the difference in time. Do you understand why? That's if we move at a constant speed. So, all right, so since nobody is saying anything, I will suggest one possible idea, okay? One idea is we need a change in time. Why not take both times to be equal to 2, because I need the velocity at 2. And then if so, I try to measure the change in position divided by change in time. There was 0 change in time, so I divide by 0. There was actually 0 change in position, so I have 0 divided by 0, okay? So I did not allow any time to change. I'm hoping that, but I need two moments of time and 2 moments of position to calculate any sort of velocity. I have 0/0. So this, first of all, that's my example here, is trying to tell you that dividing by 0 in some sense suddenly becomes important. If I could divide by 0, perhaps I could have figured out what's the speedometer. So another idea is this. You have all noticed that velocity requires some amount of time to change. Do you agree? So you press on the accelerator, right? It's not right away that you move from 0 to 60 miles an hour, right? You require some amount of time to elapse as you press on the gas. So if you give very, very little amount of time to change, there will be very little change in the velocity. So it's nearly uniform if the time intervals are really, really close, right? That's the idea. Do you follow it? I want you to respond, guys, that yes or no if you follow or not follow, because then at least I know you're part of the class.
I'm a little lost.
That's great.
Okay.
Don't worry, right? Because it's just an introduction. We're going to cover limits for quite a while, right?
All right.
So this is where you have to really think about it, guys. You have to think about velocity, okay? If you move at a constant velocity, would anybody like to explain to me? If you move at constant velocity, what is this idea? Some of you run. I mentioned this runner running at 6 miles an hour, right? When the runner is moving at completely constant speed, it's the easiest situation possible, right? If a runner is moving at constant speed, you all know, okay, in 1 hour he runs 6, then in half an hour 3, and in 2 hours 12. Okay, what is it that you are truly describing, guys? You are just comparing time and position. Do you agree? Mm-hmm. So you have an amount of time. For that amount of time, you have the same amount of position. You understand? That's why you divide. You're saying for unit of time, for a given unit of time, you always have the same position. So in other words, what you do is you distribute the distances evenly across time. Do you understand what I mean by evenly across time? That's what you do when you divide, right? It's like if I have 12 apples and I divide it among 2 individuals, I distribute the apples evenly among the 2 individuals. So let's say when I say 12 divided by 2 is 6, that's saying that 12 apples divided by 2 individuals means 6 apples per individual. That's what division is supposed to capture. So if you move constantly, if the velocity is constant, that's just saying that every uniform motion, for any interval of time, you observe the same amount of displacement, the same amount of changing from one position to the next. Okay, so you see what I'm saying. All right, so anywhere where you look, I hope you can see my fingers. Mm-hmm. Anywhere you can look, any interval of time of the same length contains the same amount of displacement. That's when the velocity is constant. Okay, and that means that, you see, if I double the time, I double the displacement. If I have the time, I have the displacement. That's why I report velocity as the ratio of displacement over time, because I want to give one number to report it. That's the constant number that captures it. But really what you really mean when you speak about velocity is that for any interval of time, you always, if it's of the same length, if any 2 intervals of time are of the same length, you have the same displacement, the same distance traveled for that same length. You understand? That's what you're truly trying to say. So you don't think that's the case? So I haven't. The smaller the time, the less the velocity. No. The smaller the distance will be. You guys listen again carefully, right? What is it that you're trying to capture with constant velocity at least, right? So it's very difficult to right away jump to variable velocity. Let's consider constant velocity. So your idea is to capture that something is happening monotonously, right? So when you say somebody is moving constantly at the speed of 6 miles an hour, what are you saying? You are saying that if you take intervals of 1 hour, no matter where you take them, so imagine that the person is running forever, infinitely long, without ever tiring, without speeding up or slowing down. That never happens in real life, but forget about real life for a moment, right? Just something is moving always in the same monotonous way. With me? Everybody with me, guys? Extremely important. That's the first main topic. I want you to really understand what's velocity, right? What is it that you're trying to explain? So monotonous motion means take any time of the day. Take 1 hour any time of the day. You will see that the person moves exactly 6 miles for that amount of time. No matter in the morning, in the evening, in the afternoon, if it's 1 hour, right? And if it's indeed constant, then if you take a shorter interval of time, if you take half an hour, you would see that any half an hour where you observe the person moving, you notice that in that half an hour, the person moved 3 miles. You understand? And if you take an interval, any interval at night, in the morning, any time of length 2 hours, you will see that the person moved 12 hours. Okay, so instead of reporting all those different times, you see what you do is you normalize it. You say 12. So you say 6 distance units per 1 unit of time, 6 miles an hour. That's what you report as. You understand? That's the same thing as if you listen to the previous lecture. The same thing is done with if you want to show that the infection is stable, the same number of people are getting infected, you need to report per unit of population, right? Or per unit of population tested, because otherwise it's meaningless. Just like with velocity, I can say, oh my God, right now he is moving at 6, and now it's 12, and now it's, I don't know, now it's 18. You see, it's meaningless because what you do is you change the interval. But the idea is if you keep the interval of time the same, the displacement ends up being always the same. Are you clear there? Now, usually velocity is not constant. That's the next concept. It's not constant. But you notice that it always requires time to change, to speed up, right? You know that from experience. Maybe very little amount of time, but it doesn't happen instantaneously. You need some amount of time to change your motion. So to slow down or speed up, you need possibly a very small amount of time, which means that if you take a very, very small increment of time, very, very tiny, then over that interval of time, the motion was essentially uniform. So if you take this interval of time and if you break it into smaller segments, you would notice that the motion over that interval was uniform. Do you understand what I mean? Or very clearly, or very close to uniform. Not quite uniform, but you make it tinier and tinier and tinier. Okay. So my first idea. So if I don't allow time to change, then the velocity is uniform. So that's why I took the same position. But the problem is that I divide by 0. I have 0 over 0, which I cannot do. I need a way around it. You understand? So if you don't allow any change in time, by this speedometer, when I take a photograph, the speedometer is showing a particular value. What is that value? I try to figure out. Okay. How can I reconstruct it? So the idea is I need 2 moments of time if the velocity is constant and the corresponding position. Since I already know the car is not moving at a constant rate, I know that you see that measurement that I did before with the runner that runs always at the same speed is not good, not quite good. But then I realize velocity requires time to change. So if I allow very little time, let's see if somebody said something. Well, we are talking right now, guys, but we're talking about only velocity in a linear direction, one-dimensional velocity. We will talk about other velocities when you move to higher math, to Calc 3 or whatnot, right? Right now, we are only measuring velocity in one direction. So here is the idea that I try next, okay? So, and this is a pretty funny idea. What I do is I cannot plug in 2 in both cases, so I plug a fake 2. I plug a fake 2. And why? Because I cannot divide by 0. I'm going to try to see what happens if I divide by a fake 0. Okay. So I will explain this idea much deeper, but this is how a certain thing began. You understand? If you don't allow any time to elapse, I'm trying to figure if there are tricks. First, it's going to be completely weird what happened here, and then we will try to explain why that will be the case all through the course. Right? This is only an introduction to velocity, but I want you to try to think about those concepts as soon as possible. So you understand? Why do I put the same moment of time in here and divide by the difference of the same moment in time? Because if you don't allow time to change, the velocity did not change, right? And I'm hoping that will give me something. But I have 0 over 0. I cannot see through it. Now let's see what happens if I plug in a fake 2. Okay, I plug in something that I'm just trying to see if I can plug a fake 2 here, and this is a real 2. I will explain what that fake is in a moment. So what happened then, evaluating x at this fake 2 will be fake 2 squared plus 1 minus 2 squared plus 1, which is the position at 2 seconds, okay? And divided by the difference in time. Now, if I simplify it, look at it, the ones, they cross out, 1 minus 1, it crosses out, and then I have a fake 2 squared minus a 2 squared, which I can factor into a difference of squared. It's fake 2 minus 2 multiplied by fake 2 plus 2. Do you understand? Just no, in terms of, forget about understanding for a moment what is that fake 2. just try to understand the algebra here, right? You see how I move from this point. So x is evaluated by taking the amount of time, squaring it, and adding 1, right? So I do this for the fake 2 and for the 2. I simplify, I get this numerator. Are you with me, guys? Write that you are with me from this point to this point, or ask me questions.
Okay, question. So real quick. So the fake 2, so x of t for 2 is 5. So when you plug that in, it's the same for the fake 2 as well?
It is, but here I'm gonna try to show you some trickery, right? So it's gonna be confusing at first, and I'll try to explain to you what's the idea of the fake 2. You understand, guys, that when you do mathematics, you are doing philosophy, right? If you have not thought of philosophy, that's in fact how I came to it, in fact, right? So you haven't thought about velocity, so you think it's understood, but then when I ask you what it is, you have a trouble giving me any explanation. So it means you kind of thought about it without the presence of your mind. It's like when you speak English, you don't think about the grammar. You just grew up speaking it, most of you, okay? But now you have to actively think about what those ideas mean. So look what happens here, right? So you understand why I did this calculation. My hope was, okay, if time changes, velocity changes. But if time doesn't change, then velocity will not change. It will be the same velocity. And so it will be constant velocity, or over an interval of length 0, it will be constant velocity, right? So what I try to do is I try to calculate the change of position, but there was no change in position, and there was no change in time, so it was 0 over 0, and the information is hidden. I cannot do it, it seems, right? So then I try this strange idea. I try, what if I plug in a fake 2, right? And I'm not sure what a fake 2 is. My goal is just not to have a 0 on the denominator, okay? And then I just do some algebra. Look at it, guys. I just plug in a fake 2. Don't simplify, by the way. Some people right away want to say 5 and those things. It's better to just see the pattern. Okay, so I just say, what is it? It's this number squared plus 1 minus 2 squared plus 1. I don't simplify it. I just cross out whatever is like. I have 1 minus 1, it crosses out. And I have now 2 fake squared minus 2 squared divided by fake 2 minus 2. Okay, and the reason I did this is because I have a fake 0. If I have a fake 0, I can simplify, I can divide them out. Look what happened here. This is a difference of squares. Do you see the difference of squares? It's a number squared minus another number squared. It's always the first number minus the second times the first number plus the second. We will learn about it more. But this is, again, algebra, guys. Hopefully, you already know it, right? Because every single thing that you don't, I need to explain. With me, guys? So look what just happened now. I cross it out, and now I have a fake 2 plus 2, and then I forget it was a fake 2, and I'm just going to say 4. So my prediction for this velocity, I'm predicting that the speedometer was pointing to 4. In other words, 4, if it's in meters, 4 meters a second. You understand? I tried to use this trickery, and with this trickery, I was able to obtain the velocity as 4.
Wait. Professor, wait.
Yeah.
Okay, just to reiterate. So what you did was cross out afterwards, and you added the fake 2 with the real 2. Okay, so how should I ask this? So it doesn't necessarily equate to 4, but it
at the moment we lied. I mean, I'm going to introduce what those things are. And basically when calculus was discovered, very big mathematicians attacked it, because it seems like, what are you doing here? You can't divide by 0, but you divide by 0, and now you have you have a 0, suddenly you don't have a 0, right? It seems very arbitrary. But this was later developed and made precise. I'm showing you, in some sense, it's still an introduction. So if you don't understand this presentation, guys, in a way it's like a semi or a pseudo-historic presentation. Pseudo because it was much worse, right? If you try to read Newton, you would go crazy, right? When a person first introduces a topic, it's like the first airplane, the first something. It's usually very complicated and sometimes unnecessarily so. In other words, you can actually make it clearer, make it more precise, and error-proof and whatnot. But that's how ideas work. You understand? So the point is, you think about something, and it's usually in the first trial not precise. but you have some sort of guiding principles. That's what I want you should have some sort of thing in your spirit, right? So it's philosophy here. I'm saying if I don't allow time to elapse, then velocity had to stay the same. So then I think, okay, so I can figure out the velocity by taking a difference of positions, but actually it's the same position. Difference of the same position minus itself divided by a difference in time. In other words, how much distance is covered by an interval of size 0. But what is that? An interval of size 0. Understand what I do? Is if the interval is of size 1, well, they can divide it. But how much is contained in an interval of size 0? And that's what I think is the speedometer showing. When I take a photograph, right, the speedometer is showing 4. So basically at that moment I took a photograph, you can imagine taking 2 photographs exactly at the same time, and we have a time interval 0. For that time interval 0, the arrow does not move away from 4. I'll explain later a bit better, right, what it is. Let's see in general what's the situation. I want to figure out what would be the velocity at any moment of time t. Okay. What is the speedometer showing, not just at t equal to 2, but what does it show in general, right? So what I do is I think of not allowing time to elapse. T hat minus t, right? Not allowing time to elapse. So the reason I do the hat is because I have to say a fake t here, so that the denominator is somewhat not 0, to avoid the problem that I cannot divide by 0. I hope you all understood why I cannot divide by 0. That's why I made the explanation there, right? It's not arbitrary. But because I cannot divide by 0, I need to figure a way out of it. So what do we have here? At x t hat, I have t hat squared plus 1. At xt, I have t squared plus 1. I simplify it, and I get t hat squared minus t squared divided by t hat minus t. And my goal is to get rid of the denominator being 0. So I factor out the numerator into t hat minus t times t hat plus t divided by t hat minus t. And then I cross out t hat minus t. You see, and when I cross them out, I have t hat plus t hat. So t hat plus tm, and this I pretend is the same. T hat is a fake t, but really I pretend it's t. So my estimate is that the velocity is always twice the time. So what I just figured, not precisely yet, right? But what I think is the following. So what is the velocity at time 0? At time 0, the velocity is 2 times 0, which is 0. The car is stationary for a moment at 0. The instantaneous velocity at 1 happens to be 2, because 2 times 1. The instantaneous velocity at 2 happens to be 4. The instantaneous velocity at 3, I predict, will be 6 meters a second. You follow? Let's see if you do. Here is your next task, guys. Let's say now try to do this, try to go through this idea, and to the best of your ability, try to explain what's happening. So we have that a particle or a car is moving with this position function. That's where it is at any given moment of time. So at 0, it's 2 units of time, 2 meters on the positive x-axis. At t equal to 1, it's minus 2 meters on the positive x-axis. So what I want you to do is find the velocity as a function of time. Given this formula, find what is the speedometer showing at any given moment of time t. You understand? Just like we did over here. Okay? And try to explain to me if you want to present it, why is it this calculation? What is this calculation according to your understanding?
Sorry, Professor, do you want us to submit our answers when we're done?
Yes, you can write the answer, and then we'll see if anybody will decide to explain to me the idea. Okay, not only if you can follow the answer is it important. I want to know, do you realize why you could have come up with such an idea on your own? Okay, one person has suggested what it might be. Let's see what the others will say. Okay. 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 Good. All right, guys, let's walk through it together. First thing is, I just didn't want to draw the car. And in fact, what we really think about is moving particles. Okay, so what I imagine is that there is a particle and attached to it is a speedometer, which I cannot see. And that is the speedometer at any time t. I mean, this in particular shows you at time 1, what's the speedometer. But in general, at any time t, anywhere at time t, there will be a speedometer will be showing something in terms of t, right? That makes sense, right, guys? So if you recorded your entire trip in your car, you can imagine that if you had a video of the inside of the car, you could see the speedometer changing. And if you moved the time, you would see at different moments of time a different speed. The arrow would point somewhere, that's for sure. So here is the idea again. We are going to select, we want to calculate x of t hat minus x of t divided by t hat minus t. And the idea is that I will select t hat. I'll say a little bit more about t hat now. Since I cannot have 0 interval, I am going to have a very short interval. So what I will do is I will move this time bar just slightly to the right. You see, I will take this time bar and I might move it slightly to the right. That will be my t hat. So if this is t, my t hat is slightly to the right, but not this amount of distance, maybe smaller. And the philosophy is what? If I gave, or if I selected only a very small increment of time, the velocity had very little chance to change. And the idea is to select even smaller and smaller and smaller. So t hat, we're going to learn in limit. It's not even a number, it's a sequence of numbers where I select smaller and smaller and smaller, and I try to predict the tendency. Because the smaller the difference in time, the less the velocity had the opportunity to change. Is it clear? And Alexa, since you participate, I really appreciate it. Is it clear to you, at least?
Yeah, it is. Like, so far it is clear.
So far, right? Just think about it, okay? It's very, yes, I hope so, right? So you understand what's the idea of the t hat? It's really philosophy, right? It's not from some algebra that I get it. It's really this idea that a t hat is essentially t, but slightly different in terms of the calculation. So that's why I first pretend it's different. And then when I cancel it, I actually pretend it's the same. Because the idea is it's a fake t. Why is it a fake t? Because it's really, really close to the actual t, and it's very difficult for you to tell them apart. But if you have two different moments of time, you don't divide by 0. And if you have two different moments of time, you are calculating, it's called average velocity, by the way, right? But we'll learn only at the end of the class, possibly why it's called average, what's the average about. But the idea is that it's nearly constant. So if I change the time just slightly, the velocity is nearly the same through all this time. In other words, if I divide it more into segments, it will look like it's moving at a constant speed from here to here. You would not see, if I play this video and watch the speedometer from here to very small amount of time, I will not notice any difference in the speedometer. Understand? It's just because the difference is existing, but it's very gradual. If I move from here to here, then I would notice possibly right away that there is a difference in the speedometer.
Okay.
So that's the idea, that things are gradual. So then if I do the calculation, I plug in t hat, it's minus 4 t hat plus 2, minus 40 squared plus 2, and I can cancel all the 2's. And I group things together, I factor out the minus 4, and I get minus 4 t hat squared minus t squared divided by t hat minus t. Then I factor out the difference of squares. This is t hat minus t times t hat plus t. That's because difference of squares, a squared minus b squared is a minus b times a plus b. So I have this, and then I can cross out with the denominator. And I have minus 4 t hat plus t. Yes, make sense?
Okay. Yeah.
Yes. And then what I do is, because t hat is so similar to t, I no longer have the 0. I now see that it's 2t, and that's why I have minus 8t. So my velocity, my prediction is velocity is always minus 8 multiplied by the time.
Got it.
Okay. So you understand what I reasoned, right? So that's again the remark here, as I just mentioned it already a few times. And in particular, the instantaneous velocity, what the speedometer is pointing at t equal to 1. This would be just minus 8 times 1, which is therefore minus 8. And so if it's minus 8, the car is moving in which direction? What is the person pressing? So what gear?
Brake.
Well, reverse actually.
Oh.
Reverse, because the velocity is negative, right? So at 1, it's minus 8, so that means I'm moving in reverse. Okay. Wonderful. And Yes, Alexa, I tremendously appreciate your participation, right? So the others are silent. If you're confused, you're actually possibly helping the others. The others just don't bother talking to me. Okay. You see, so what is this this t hat? This t hat is really not one approximation, but it's a sequence of approximation. It's something that you call, it's striving to be t. Okay, so in the striving to be t, we are talking about limits. Okay, so we have in calculus two notions of evaluating a function. We can possibly evaluate a function at some number c, or we can take limit as x goes to c of this function. Okay, so this first notion, I think you already know, right? So you just take a function, you plug in a number, and then the function processes this number and spits out a value. What you do in the limit, you don't plug the value c, but you plug many values that are not c but very similar to it. Okay, so that's the difference between this operation and that operation. This means plug in numbers, but not one number, rather than that, many numbers that are not c but very close to it. Okay, let me show you what that means. So yes, it's approaching c, or trying to approach, if you like to say. So here is what we have here. You see, if the function is 2 times x, so what the function is doing, it multiplies the number that you put in by 2. If I put in -1, I just get -2. Okay, what do I do if I ask limit as x goes to -1 of this function? What I do is I select possibly a sequence of approximation. I cannot select -1, so maybe I'll select -1.1, -1.01, -1.001. I select a bunch of numbers that tend to be more and more like -1, but never actually -1. And not one number, but infinitely many. And then I try to predict the pattern. If I multiply this number by 2, I get -2.2. Right? If I multiply this number by 2, I get -2.02 or -2.002. And you can see this number is tending to 1. And as it happens, what do I get here? I get something that looks more and more like -2. So we will say that the limit is also equal to -2. I end up with the same answer if I plugged in the number -1 or if I take this process. Okay, but the difference is this, the process, right? So when I ask for the limit, I'm asking for this process. Okay, I'll show you examples of when that's the limit is not equal to plugging in the value. So for example, here, would you like to try to do the calculation, guys? So here, f of x equals to x squared plus 1 when x is not equal to -1, but when x is -1, the answer is 3. So clearly, if I plug in -1, I simply get 3. What happens if I take limit as x goes to -1 of f of x? You understand what happens if I plug in values that are ever closer to -1 instead of x here, but never -1? What values am I going to get? What is it tending to?
What was the question again?
The
One more
question is
time.
calculate limit. So we know that f of this function, the function is defined to be, when I plug in -1, the function is defined to give me 3, right? But when I take limit as x goes to -1, this thing, right? What is the limit going to be? Question is figure out what this is.
Okay, so for anything that's not -1.
So that means what? What this limit means, I plug in values instead of x, but I do not plug -1. I plug things that are better and better approximation of -1, but never actually equal to -1. You understand?
Okay.
Just like in this table, I plug in possibly -1.01, right? -1.000001. I plug in numbers that are very, very close to -1, but not actually being -1. What do I get?
So you would get 2.0001.
Yes, and the limit is you're trying to predict what is this becoming, right? So here you never actually get -2, but you see that it looks more and more like 2. The closer the number is to -1 in the previous example, the more the answer is like 2. What about this example? right? So
Oh.
here is the table, right? And a bunch of people said also 2, right? Because this here I decided maybe I'll put minus 0.99 or minus 0.999, right? So those numbers are ever better approximation of -1. As I plug them in, you might predict that what I'm getting is here is the actual calculation. It looks more and more like 2.
Okay,
And
so it is
in some
2.
case, because this is a simple expression, you might imagine if I square a -1 like number and add 1, I get 2 like number. If this number is very, very close to -1, then essentially it's -1 squared plus 1. So you expect it to be 2. But notice the difference. So here the function is equal to 3 at -1, but the limit is equal to 2. Because you see what I do here, I plug in numbers not equal to 2, but close to it.
Got it.
Good, wonderful. So that's a table way of thinking about it. I will explain what the limit is more generally, but I think today we are out of time, right? It's already 12:04. We are done at 12:05. If you want to talk about something, guys, how many of you have watched the videos I suggested or thought about the first lecture again? Right, yes or no? I just want to know what sort of things interest you. All right, well, yes, I posted, I think I sent you a video, right? If you want to, if you're interested. So let's just see before you go, guys, perhaps you tell me how many of you want to study medicine or something related to it, just so I have a gauge. I think if you are studying medicine, guys, certainly you should look into it, right? Look at what this person is saying. It should be interesting to you. If not, then you are not possibly interested in medicine. Well, so the lecture is over for today. You are free to go. If you want to stay for discussions, for office hours and whatnot, we can talk about anything you like, not necessarily this material.
Professor, I was wondering where you would find the worksheets on your website. Would it be under Math 150?
Yes, everything under Math 150 for this class.